Okay, so first of all, I would like to thank the organizers for the invitation to speak here. It's actually my first time in Asia, and so far it's great. So indeed, I'll tell you about some work in which we explore this interplay between non-invariable symmetries and scattering amplitudes. So to start with some motivation, I think we all agree in this room that symmetries and their anomalies are key concepts in physics. They give us strong constraints on the dynamics of UFT. So for instance, they tell us which terms we can write down in an effective Lucia Lagrangian. And these concepts have been refined and generalized in the past years. So now we have this notion of having topological operators, which allows you to write higher form and non-invariable symmetries. So the question we're trying to answer here is, what are the implications of these generalized symmetries on scattering amplitudes? So there are two punchlines for this talk. The first one is that crossing symmetry of the S matrix is modified in the presence of certain non-invariable symmetry. And the second one is that you can actually use these symmetries to give some concrete numerical predictions and explore new corners of the space of quantum field theories. So even though we expect this to be true in general, the explicit checks with it were in 1+1 dimensions. Okay, so as an appetizer and a good example to keep in mind in the rest of the talk, let me tell you about a specific RG flow. That is a flow from true critical easing, which is the second unitary minimal model, into a gapped phase. So if you deform this minimal model with this phi13 operator, depending on the sign of the deformation, you either flow into the previous minimal model, that is critical easing, or to a gapped phase where you have 3 degenerate vacua. So the type of amplitudes we will study are the scattering of kinks that interpolate between these vacua, which I label by A, B, C, D. And this amplitude depends on, of course, the momenta and the Mandelstam invariance. In this 2-to-2 case, only S, or theta, the rapidity. And we expect various properties to be satisfied in this case, among which we have this crossing symmetry. So you send S to T or theta to I pi minus theta. So this flow was studied a long time ago, and actually the S matrix was bootstrapped because this flow is iterable. So Samologikov found an exact amplitude describing this RG flow. And this is the equation he gets. So there is some unimportant factor here, then some phase that depends on these coefficients D that depend on the vacua. And then you have these two terms that tell you which vacuum configurations are allowed and that get exchanged with this crossing theta to I pi minus theta. So this is compatible with everything they knew at the moment, so back in '89. But nowadays, we know that along this flow, you have other global symmetries. So in particular, there is this non-invariable symmetry N, that what it does in terms of the vacua is that it maps adjacent vacua. And to our surprise, if you compute the word identities for this non-invariable symmetry, you see that this amplitude is not compatible with those. So it doesn't commute with this symmetry. And instead, if you bootstrap again this amplitude using the fact that you should have this non-invariable symmetry, and again, unitarity and iterability, you get this other amplitude, which looks similar, but it's not the same. And the price to pay is that you need to modify crossing. So now you have this square root here with these coefficients T that are called quantum dimensions. So this is an appetizer. In the rest of the talk, I will give you details to understand this example and other things. So let's see the outline. First, I will describe very briefly what are fusion categories and some examples realized in minimal models. Then I will tell you more about these kink scatterings and how we can derive modified crossing. And finally, I will tell you how we can use this to explore the space of general QFTs. So starting with the first part, generalized symmetries. So the modern notion of what symmetries are in QFT is that they are given by topological operators. That is that you can move freely in space-time. And in particular, if you move them in time, it gives you the charge conservation you know well. So with this perspective, the usual group symmetries are now called zero-form invertible. So zero-form because they act on local operators. And you can also fuse these topological operators following the group multiplication law into a third one. And you're also requiring for group symmetries that there is an inverse, so that each element has an inverse and you can undo whatever you were doing before. So this is what we knew already. But now with this topological operator picture, you can generalize symmetries in various ways. So there are higher form symmetries that act on extended objects. I think you heard from Julio about them. And there are also non-invariable symmetries where you're not requiring these inverse properties. So what I will discuss here are zero-form symmetries in 1+1 dimensions, where the topological operators are lines that I call L. And the mathematical framework to describe them is called fusion category. So what is the data that describes a fusion category? You have a list of objects. In this case, it will be the topological lines. You have fusion coefficients that tell you how you can fuse two lines together. So note that here we have a sum, so it's already more general than a group structure. And we're also not requiring an inverse. So we're going beyond group symmetry. And to make contact with the appetizer, the expectation value of a loop of this topological line is precisely this quantum dimension I wrote before. And the final ingredient are F symbols, which tell you how you can relate different ways of fusing lines together. I will also write these tetrahedral symbols that are proportional. So some examples. First, the familiar Z2 discrete group. Here you would have two topological lines, the identity and this eta line that squares to 1, so it's invertible, and the quantum dimension is 1. A generalization of that is the Z2 Tambara-Yamagami fusion category, where you have the same eta line, but now you also have this non-invariable line N with this fusion rule and a quantum dimension that is square root of 2. And the simplest non-invariable fusion category is this Fibonacci one, where you have two lines. One of them is non-invariable with this fusion rule and quantum dimension. So the last thing I want to say in this slide is that often these non-invariable symmetries actually imply that you cannot have a trivially gapped space with just one vacuum. And what we will study here are precisely RG flows where you have these symmetries that are anomalous in this sense that lead to the generate vacua in the IR. So as we study the King scattering. Okay, so let's see some theories where these symmetries are realized. And a simple example are minimal models. There, it is known very well what the topological lines are. They're called Berlinde lines, and they have the same fusion algebra as the primaries. And they act on the primaries in this way, where this is the modular S matrix of the CFD. So starting with the simplest minimal model, you have critical easing with three primary operators. So this gives you three symmetry lines that are precisely this Z2 Tambara-Yamagami category. And this N line is something that you might have heard of already. It's related to this Kramers-Vanier duality. So if you remember, if you put the Ising model at different temperatures, you have an ordered and disordered phase. And there is a duality between these low and high temperature phases that is actually a symmetry at the critical point. So this is the non-invariable line N. And here I wrote what it does for the primary operators. So it gives you a sign for epsilon, and it maps the spin operator into a disordered operator that lives in this twisted Hilbert phase. So let's go into the next one, which is the one we discussed in the appetizer. So here in true critical easing, we have 6 symmetry lines. And you can deform the CFT by different operators, and this will preserve different lines. So for instance, with this 513 deformation, we preserve exactly the easing category, as you expect from this RG flow. And if you deform with this 5-1 deformation, you preserve these two lines that form the Fibonacci category. Sorry, I want to say something else. And the fact of having these three degenerate vacua, what it's actually telling you is that you have a spontaneous symmetry breaking of the three symmetries that are present along the flow. And as I said, this non-invariable line maps adjacent vacua, whereas this eta1 maps the left to right. So there is a generalization of these 513 deformations, and the flow looks like this. With one sign, you flow into the previous minimal model. And with the other one, you flow into a gapped phase with n-1 vacua. And the lines that are preserved here form what is called an AN fusion category that will appear in the bootstrap. Okay, and finally, these three deformations are known to be interrobable, which is nice because you can actually write down an exact non-perturbative S matrix for them and do checks with them. So this is for the first part. Now let me go into the scattering amplitudes. So as I said, we will be discussing this 2-2 amplitude for the kinks that interpolate between the different vacua. A, B, C, D are the label for the vacua. And it depends on Mandelstam S or this rapidity theta. So what are the axioms we expect this amplitude to satisfy? First, we have unitarity that tells you that the modulus squared of this amplitude for physical values of energies is bounded by 1. Then naively, you expect this crossing condition where you exchange one of the in and out states. So you send S and C channel. Then if you know you have some global symmetries there, you should have some word identities for the amplitudes. So something like this. And finally, in case that your theory is interrobable, you should test or apply these Yang-Baxter equations, which tell you that higher point particle amplitudes are factorized into a sequence of 2-2, and you can do it in different orders. So with these axioms in mind, let's revisit these 513 flows and the computation by Zamologica. So what he did was to impose unitarity, these crossing conditions, and interability, since he didn't know about most of the symmetries here. And what he found is this expression that, again, has this phase here where you have the quantum dimensions, and these two terms that get exchanged under crossing. But it doesn't commute with the non-invariable symmetries. So what this means is that these axioms are mutually incompatible for these non-invariable symmetries. So instead, if you use unitarity, these Yang-Baxter equations, and the word identities, what you get is this expression, which is basically the same without this phase here, which was weird anyway, because it gives you some oscillating factor in energy. But of course, something has to give, and what gives is crossing. So now you have this equation here, where you need to pay these square roots of the quantum dimensions, and you can see clearly that it arises from crossing with these two terms. So this is one particular example, but we actually have an understanding of why this should be true in general without alluding to interability or anything else. So let's revisit that. So these new crossing rules can be understood from the proper normalization of your in and out states, taking into account that now the IR has some topological degrees of freedom. So the amplitude is this overlap between in and out states. So you can prepare some in state with some boundary conditions, DCV for your vacuum, and then the out state would have DAB for the vacua. And this amplitude I'm describing here is precisely the overlap modulo some momentum conserving delta function. And naively, I can just do a path integral in Euclidean signature, and this is just crossing symmetric, so what's going on? And the point here is that in order to have unitarity of the amplitude, we should normalize our in and out states to 1, but with the momentum conserving delta functions. And to do this, we can use what we know about the TQFT data. So we know that if we're in this case in which we break spontaneously all symmetries, we can identify the vacua with symmetry lines. So in mathematical words, this is the regular model category. And then also that our kink acts as a symmetry line itself. So in this flow from tree critical, it acts as the non-invariable line that maps adjacent vacua. So with this input, you can compute the norms of your in and out states, say in the S channel. So you would need to evaluate this network of topological lines where the kink lines are here appearing vertically. And similarly for the out state, so that when you define the S matrix, you would divide by these factors here so that you have the properly normalized states. And what's crucial here is that they actually change if you go into the T channel. So you would need to evaluate these diagrams with these V lines going horizontally. And this is how you get this crossing modification with the amplitudes that is taking into account these non-trivial factors that you get from the TQFT in the IR. And you can see that this evaluates precisely to these quantum dimensions in the cases I mentioned earlier. So this is the physics argument for why this should be true in general. Now let's put it into practice and do some S-matrix bootstrap. So we will stick to this 2-to-2 scattering of kinks. And what we want to do is to bootstrap the space of QFTs with a given fusion category. So the key point here is to somehow trivialize the fact that you need to obey these word identities for your global symmetries. And what you can do is to use projectors into a given fusion channel. So for the case I'm discussing with all the symmetries being spontaneously broken, this projector is simply written in terms of the F symbols of the category. And then we can write the rest of the axioms for these partial amplitudes A chi into a given fusion channel. So unitarity is simply written in this way. Then our modified crossing condition for the amplitude looks like this for the partial amplitudes A chi. And something I didn't mention before, but of course, we're also assuming some analyticity. So these amplitudes are analytic in the complex S plane, except for singularities related to poles, multi-particle cuts, etc. So the bootstrap problem we want to solve is given a fusion category, where is a space of allowed partial amplitudes we can have. And there's a machinery to solve this problem. So you can, for instance, write an ansatz that trivializes analyticity, modified crossing, and the symmetries, impose unitarity numerically in a grid of points. And then you want to bound some parameter, you can choose what to bound. So for instance, you can maximize functionals of this type and explore the space of partial amplitudes at a given energy. So I'll show you 2 examples. But let me review the setup here. So we're dealing with massive QFTs with a given categorical symmetry, parameterized by these topological lines L. And what we're scattering are kinks that interpolate between the different vacua you have in the IR. And we are bootstrapping this amplitude, assuming 2 things: the minimum spectrum required by symmetry, and this breaking of all symmetries so that the number of vacua is the same as the number of topological lines. And these are 2 categories, AN and Fibonacci. So the input here is that we have n-1 topological lines and vacua. There are 2 fusion channels given by this fusion rule here. So we have 2 amplitudes that we need to bootstrap. This is an example of an allowed configuration of the vacua. And your kinks interpolate between vacua that differ by 1/2. And this is an exclusion plot you can get. So these are the two allowed partial amplitudes at a given energy. Everything outside is ruled out. It's not compatible with these principles. And inside, it's allowed. So you see that for different ends, you get similar shapes. And these vertices here are actually iterable. And the lower one is precisely these deformations of minimal models by phi-1,3 operators. So that's for AN. Then for Fibonacci, you can do something similar. Here, if you recall, there were two lines. So we are inputting two different vacua. We have two fusion channels. But now, because of this cubic coupling, you can have these other configurations where you have kinks with the same vacua 1/2 on both sides, so a breather. And this you can interpret as a bound state of the other kinks. So in one of the channels, you actually have a bound state pole, and you can play with this parameter G, the cubic coupling. So now we can write, do some numerical computations to get this 3D shape, where we have the cubic coupling and the two partial amplitudes at a given energy. And you find this peak here. And some of the costs are known models. So you have, for instance, this deformation of tricritical easing studied by Smirnov, and also the formation of 3-state pots appearing here as vertices in this space. So we did not input interability. It arises at special points in the boundary. And some of them correspond to known models. And also comparing to group like Bootstrap, what we see is that we don't have these sort of oscillations in energy, which is nice. And finally, I wanted to talk about some ongoing research in which I studied this more exotic category called Hagerup. So here we have 6 topological lines with these non-trivial fusion rules. 3 of them are non-invariable. And what is very interesting about it is that there is no known field theory realization for it. So before we had all these examples with minimal models, but here we don't know almost anything. There are some hints that there might be CFTs with these central charges, but there is no known actual model. So by now you know how it works. I input 6 vacua. You have 4 fusion channels here from this fusion rule. Then there are many kinks you can write down, including a breather, as in Fibonacci. So the parameters I bound are, again, this cubic coupling and 2 crossing symmetric combinations of the partial amplitudes. And you get something like this, so this interesting 3D shape. And what's very promising is that these vertices seem to be iterable as well. And I'm working out the analytic solutions for those. So what I have to say here is stay tuned. There's still a lot of to uncover in this phase. And okay, we'll finalize with some summary. So I told you there were 2 punchlines. The first one is that non-invariable symmetries imply for this kink scattering that crossing should be modified in this way. And this is generic for when the IR is described by a non-trivial TQFT, and the modification arises from corrections to the in and out norms. Then the second part, I told you how you can do S matrix bootstrap with these symmetries and get some non-iterable models at special points for well-known categories. For Hagerup, new models are expected. I didn't have time to talk about it, but we also understand how to input other symmetry breaking patterns. So now you need to deal with these module categories. And there are many future directions. I will just flash them here, but of course, a goal would be to understand how this works in higher dimensions. And finally, if we can see this as a toy model for understanding soft dynamics in gravity and gauge theory. So thank you.